Hey everyone, my name is Alex, and I will be talking about, I'm going to do a deep dive into Ray's scheduling policy in this talk. So, a little bit about me. I'm a software engineer at Anyscale, and as part of that, my job here, I work a lot on the Ray core, and in particular, I've been focusing a lot on the Ray's scheduler and a lot of the peripheral components around it. So this talk will naturally be pretty technical, but I'm hoping that there's some interesting things that you can take away, no matter how much experience you have with Ray. So if you're just getting started with Ray or deciding whether or not you want to use it, hopefully this talk will give you some insight into some of the things that you may want to look for in Ray's scheduler, or some interesting points that you may want to compare if you're thinking about using any other distributed systems. For the average Ray user, I think this talk will hopefully give you a good idea of the types of optimizations and benefits that you can get just by using Ray for free, even if you're not a distributed systems expert. And finally, I know there will be a couple of you out there that are like really power users and really want to get into the details of how Ray's scheduler works. And hopefully this talk will give you a much better idea of the architecture and maybe allow you to, design better applications to squeeze every last ounce of juice out of Ray. All right. So for this talk, I think we'll try to, start out by sort of framing where Ray fits into sort of the, ecosystem of other distributed systems, and how it compares to like a lot of other schedulers you may have heard of. Then we'll talk about sort of the scheduling problem and how we frame it in Ray, why it matters, and then we'll take a look at how we sort of, take those requirements and build a scheduler out of it, and take a look at some of the most important, or at least in my opinion, some of the most important optimizations that Ray's scheduler has. Okay, so to start with, I want to kind of sort of compare Ray to a couple other schedulers that you may have heard of before. So in particular, the Linux kernel scheduler, which you're almost certainly using, whether you really think about it or not, and some other systems that you may have heard of, like Kubernetes and Spark. So we'll start by taking a look at sort of the Linux scheduler. So the Linux scheduler is, in many ways, you may not think about it, or if you do think about it, it's typically what you think of when you think of a scheduler. So it obviously only works on a single node, which is sort of like the main drawback, but it sort of provides everything else that you'd expect. So when you're using threads or multiprocessing in Python, the Linux scheduler is really doing the bulk of the work there. And so it's a very, very general purpose scheduler. It has extremely low overhead, think in terms of like nanoseconds, and it is able to provide strong resource isolation because it has a lot of control over the hardware it runs on. And so like in a lot of ways, when we're developing distributed applications with Ray, like our goal is to allow you to program as if you're programming on a single laptop. And so in a lot of ways, like we want to sort of try to get as close as possible to this like sort of single node Linux experience as possible. But obviously we want to do it across an entire cluster. So another scheduler or system you may have heard of is Kubernetes. And Kubernetes is a great example of sort of a very coarse-grained resource scheduler. So you can define how many resources your pods have, and Kubernetes will do all the work to like launch those pods and schedule them on the nodes it wants to. And so this is a like really great scheduler for certain things because it's really, really robust. It uses etcd as a very reliable store. And it's really great if what you're trying to schedule is something like pods, which you don't typically have to schedule too many of them, so it's relatively like low throughput. And so like it has its like really great uses. And so because it has like these low throughput properties, we wouldn't think of it as competing with Ray. Like we think that Ray can complement it. And so in fact, like the way we typically use Kubernetes is, when people run a Ray cluster on Kubernetes, we let the Kubernetes scheduler do a lot of the work in scheduling Ray nodes. So it's not quite fast enough to schedule, a Ray task or anything like that, but it's still useful enough to schedule a Ray node, which Ray nodes may go up and down, but they typically don't do that like many times a second. And so, yeah. All right. Another scheduler you may have heard of is Spark. And so Spark is a great example of a centralized static scheduler. And so this is really, really, really great when it works. And so you'll see these in a lot of special purpose systems, especially in the data processing space. So Spark is like sort of the canonical example of this. Dask has a similar design. And these types of schedulers are really, really great when you have a special purpose workload that you can make a lot of assumptions on, because it allows you to do things like query planning and do a lot of optimizations that may not actually work super well on a general purpose system. And so, again, like I think these schedulers have like really, really great properties. And ideally, we want you to use them on top of Ray. And so like Dask on Ray is like an example of using Dask scheduler to sort of generate its static task graph, but then use Ray to actually execute that graph. And so ideally, you can get the best of both worlds that way. RayDP is a Ray data processing project, and it currently lets you run an entire Spark cluster on top of Ray. And so with RayDP, you can take advantage of your Spark scheduler and get all the great optimization benefits out of it, but not be fully constrained to the special purpose workloads that Spark can handle. Okay, so now that we've taken a look at these schedulers, let's talk about like what Ray scheduler is meant to be. So Ray is meant to be a distributed dynamic scheduler, and so this means that like the task graph can be like constructed dynamically on the fly, and it's meant to be much more general purpose and have low overhead, and we want to be able to scale to be able to handle hundreds of thousands of tasks per second. So this is just a brief summary of the schedulers we've talked about. And so, like ideally, we want to be able to interact with all these schedulers and sort of like pretend to be like the Linux scheduler in a lot of ways, but still have the scalability benefit of like not being limited to a single node. Okay, so that was a little bit about other schedulers and how Ray sort of compares and fits in with them. So let's talk about like scheduling as we think about it in Ray. And so like I think one easy way of doing that may be to sort of like take a look at a concrete example. So like one common workload, so like first, let's talk about what like the scheduling problem is. So scheduling is essentially like solving a couple of problems. Like given a task or an actor, we want to figure out like which node and like which like worker process on a node we can run that task or actor in. We also want to think about like when we run it, because sometimes we may try to, a user may try to schedule more tasks that require more resources than are available in the cluster, in which case, we have to pick which ones we want to run first, or maybe these tasks have dependencies. And finally, it's going to be really important that we solve this problem at scale. So one concrete example of this is, you can imagine like one real world example that one of our users at Amazon had is sort of the example of like trying to do some data processing job using Dask on Ray. And so like the type of job we're talking about here is like, you have 3 petabytes of input data. You want to do a sliding window operation on each like sort of row of this tensor, and then write like a pretty massive output. So the sort of task graph that you get out of that will like look something like this. You have a bunch of different tasks that all depend on other tasks. And this is sort of like an example of part of the workload, but you can imagine that this is actually like millions of times larger. And so the job of Ray here will be essentially to like take all of these tasks and figure out what the right order to run them is and where we want to run these tasks. So in terms of scale, Ray we've begun to publish a scalability envelope with Ray. These are not necessarily the hard limits that you can run a Ray cluster with. We know that there are actually people who are running larger clusters, but these are sort of this is sort of an example of the scale that we typically test Ray at and try to guarantee it'll work really well at. And so you can go to our GitHub page and like take a look at this page, and we try our best to keep this updated live. And so these are the numbers as of recording this talk, but I would encourage you to go check out this page and see the numbers, and like we would expect that all of these numbers will hopefully increase, and Ray will continue to operate at higher and higher scales. Okay. So that is scheduling. Now let's take a look at like how the Ray scheduler works, and how do we like actually build a scheduler that meets these requirements? Okay, so before we do that, let's take a brief look at Ray's architecture. So You may have seen very similar figures to this before, but essentially Ray consists of a bunch of nodes that are essentially identical, and then a global control store, which we call GCS, that typically lives on just one of the nodes, and that's the node that we refer to as the head node. Okay, so a node has a couple of important things. First of all, it has a bunch of worker processes, and these are the processes that are actually responsible for executing your task or actor. It also has a driver. A driver is just a special worker. And so in a lot of this presentation, we're going to talk about the driver as like the thing that submits tasks. Any worker can submit tasks, but we'll just pretend that the task is always submitted by the driver for now, just for the sake of clarity. Nodes also have a raylet. There's a single raylet process per node, and the raylet process is responsible for managing the resources of a node, as well as the worker processes on the node. And then finally, there's a global control store, and this you can think of this as like the single central process in Ray. And so because it's centralized, we're going to want to make sure that we're careful to not introduce a lot of bottlenecks here and keep it out of sort of like the critical path of scheduling. But it is a really convenient place to track cluster-wide properties and things like that. Okay. So let's take a look. So for most of this presentation, I want to try to follow a single simple example that I think can do a good job of sort of illustrating like this Ray scheduler and a lot of the optimizations it has. And so like in this example, we have a gradient descent algorithm. And so like what this will do is, we have a function that takes a step, takes in some data and takes in some weights. And then for each batch in our data, we'll launch a new remote task to calculate the gradient over that batch. And then finally, we'll have a combining task that is responsible for taking all of those gradients of each chunk and combining them together into like a single gradient that we can then like update and return. Okay, so here's what the task graph for that sort of looks like. So the driver, and again, the driver doesn't actually have to be a driver. It can be any worker process. It will launch a couple of tasks that are responsible for calculating the gradient. These tasks will generate some objects that are the gradients for the individual chunks that they were calculating. Then the driver will launch a new task that will be responsible for combining these gradients. It'll receive all of the gradients and combine them and generate a result. So this is sort of what the dependency graph view of scheduling would look like. From the perspective of sort of like how we're actually going to schedule these on nodes, it might look something like this. So we'll start with the driver again. It'll launch, a calculate gradient task, maybe on the same node, but like maybe this node runs out of space. So now we'll probably want to launch all of the other calculate gradient tasks on another node so that they can still run in parallel. And then finally, because now like most of our results are on node 2, like ideally we would even want to schedule our combined task on that node to avoid having to like transfer all of our gradients over the network. Okay, so now let's take a look at how Ray's scheduler will do this. So Ray uses a distributed scheduler to avoid having centralized bottlenecks. And so like let's first just take an example of like how are we going to run like a single one of these calculate gradient tasks. Okay, so the general process for this goes along the lines of iterative querying. So the first thing that a worker will do is it'll talk to its like local raylet, or it'll talk to a raylet and ask for a worker process to run that task on. So, just for the sake of, illustrating sort of the longer path for Ray, let's pretend that this raylet does not have any available workers. So the raylet will send a spillback to the requesting worker, and the spillback will essentially tell the worker that it needs to query a different raylet in order to like find a worker. So in this case, the raylet on node 1 is going to refer us to the raylet on node 2. So now we'll do that same process again and ask the raylet on node 2 if we can get a worker process here for running the task. The raylet on node 2, in this case, let's just pretend that it does have a worker available. It will then respond with a worker address. Now, it is possible that like raylet, that node 2 does not actually have any available workers. And, you could keep repeating steps 2 and 3 a bunch. But let's say it does have a worker available. It'll send an address to that worker, to our requesting worker, and our two workers can now just directly communicate with each other in order to execute a task. And so now, presumably, like now that we've done this, we can now just run our calculate gradient task because we're communicating directly with the worker that will run it. Okay, so there were like 5 steps there, and we want to do this for every single batch in a data set. So that's a lot of requests, right? Because we have to repeat that like 5-step process every single time. It would be really great if we could have a way of speeding that up. And so that's going to get us into our first optimization, which we call leasing. And so leasing is essentially what allows us to reuse workers. So let's take a look at how we can apply this leasing optimization to reuse workers. So the idea here is that when you lease a worker, you keep control over that worker, and you can do whatever you want with it and execute whatever tasks you want on that worker. So let's skip through some of the the similar parts to the previous step. So like let's pretend we ask our local raylet for a lease, and it spills us back to node 2, and then we request a lease from node 2. So now the raylet will grant us a lease for the worker instead of just like letting us execute a single task on that worker. We'll then again communicate directly with that worker and send it a task to execute. But now the difference here is that after this task finishes, we still have the lease on the worker and we can keep reusing it. And so now for the second task that we have, we can just directly reuse that worker and we don't have to repeat that entire 5-step process. And so if you have a lot of small tasks, this will save a lot of time because a lot of these requests we were doing were over a network and could like really increase the latency of submitting tasks. So just for a little bit of context, a typical lease is for as long as the task takes to execute, or like up to a couple hundred milliseconds, whichever is longer. And so like that really helps us out with short tasks. But like leases will expire, and after a while, you probably do want to keep talking to your raylets to get like potentially better places to run your tasks. All right. So that was leasing. The other topic, one of the other topics I want to talk about here is the actual like scheduling policy, or like that spillback policy, which is I think typically what people think of when they think of scheduling policy. Okay. So the spillback policy was essentially like, if you recall a couple minutes ago when we were talking about our scheduler, we sort of said that like that node 1 will spill back to node 2. And so the spillback policy here is essentially just answering the question of why did we pick node 2 there, right? There could be many other nodes in our cluster. Like why do we pick whichever node that we pick? And so like in order to understand that, I think we need to first take a step back and take a look at what a raylet has. So like we mentioned before, a raylet has a local view of, or manages all of the local resources on its node. So it'll keep like a table of all of the resources on the node. And it's also responsible for managing the workers, which we typically call the worker pool. So the raylet will take its local resource view, and every once in a while, like on the order of 100 milliseconds, will send off the like local available resources on the node to GCS. And remember, every node has a raylet, and every raylet will be doing the same thing. And so because of this, GCS will now have a semi-up-to-date view of all the resource utilization in the cluster. And so GCS can now broadcast that view of all the resources on the other nodes in the cluster back to the raylet. And so in this way, like a raylet can now actually have a like semi-up-to-date view of like what resources are available in the rest of the cluster. And so like by taking information like that into account, we can now like use that information to pick a good node for scheduling a task. Okay. So the other thing a raylet will have is a queue of like lease requests. These are the requests that the workers have been sending in. And so we can take all this information into account. And this is what we would consider our scheduling policy. And then this policy will tell us whether or not we can lease a worker or which node we need to spill back to. Okay, so I don't want to get into the exact details of our scheduling policy because this is something that's constantly changing. We're always trying to improve it so that our scheduler works better for different workloads. And so instead, I think I want to just briefly talk a little bit about some of the principles that we consider when scheduling. So like, like there's one like really common thing that we tend to think about with scheduling is sort of the idea of like load balancing versus locality. So if we, wanted to if we load balanced all of these calculate gradient tasks, that would like make a lot of sense because it would quickly distribute these tasks across the cluster. You can avoid like a bunch of types of interference that are like really, really, really hard to avoid and nearly impossible to. Like there are things like CPU cache coherence that you like arguably don't even want to avoid because the impacts of avoiding it would be worse than dealing with it. There's other things like object spilling, and so like for that reason, like for a lot of types of workloads, like people typically default to load balancing. But on the other hand, because people use Ray a lot for things like machine learning, if we were to load balance all of our tasks to different nodes, that would mean that combined step we have to do later is going to have to fetch a bunch of gradients from a bunch of different nodes, and that would require like a lot of network cost. And so like we may not fully want to load balance. So there will be a blog post about, sort of about like a lot of the work that we've done in scheduling with a lot more data on this topic. It's going to come out on the Anyscale blog. So I would encourage you to check out the Anyscale blog and keep a watch out for that blog post if you're like really, really interested in some of the experiments that we've run and how we've designed the policy that we use today. Okay, the final like really important optimization I want to talk about here is data locality. So data locality is essentially answering the problem of, like we had this like combine gradients like operation that we did that takes in a bunch of gradients. So we could in theory run this task on any node in the cluster and we would get a correctness guarantee. But it would be really, really great if we could run this task where a bunch of our gradients already live, so that we don't have to like download them all onto some remote node. So the way that we handle this is through something we call locality-aware leasing. And so this takes advantage of a couple of things. So one thing it takes advantage of is the fact that essentially in Ray, objects are owned by the task or by the like worker that created them. And so if you've never heard of ownership before, that's perfectly fine. Just know that an object and the information about an object and all of its metadata lives on the worker that creates the object. If you want to learn more about ownership, Stephanie, another engineer at Anyscale and a PhD student at Berkeley, wrote a great paper on this and presented it at NSDI this year. And I've put a link to that at the bottom of these slides. So I would encourage you to check that out if you really want to learn more about the details of ownership. Okay, but workers own the objects that they create. And workers can already send lease requests to any Raylet, right? Because they had to be able to for that spillback policy to work. So one thing we could do here to get data locality is essentially to say like, okay, well, like on this worker, we know where all the objects are. We can control where we send our lease requests to. So instead of sending a lease request to our local Raylet, like why don't we just start out by being smart and sending our lease request to the correct Raylet? Okay, so let's take a look at how this works. So here we have like a diagram of what a single worker looks like. There's some code that lives in Python land. That's the blue section, and that's where like you're actually calling combine.remote. And below that is sort of the rest of like the Ray core worker. So what's going to happen, and this core worker is what contains the object directory and like all the information about each node or each object and where it lives. So what we're going to do here is when you call something like combine.remote, we're going to take that request and we're going to queue it in a like task queue. Then as our like calculate gradient operations finish, this like directory of all of our objects will begin to be populated and we'll get the node locations that each object live on. So once all of these objects have been resolved, we'll have all the information we need. And we can use a leasing policy that will take into account, like that specific task and all of the objects it depends on. And it'll pick a node, ideally the node that would require downloading the least amount of data. And then we'll queue up a lease request to send out. And, like maybe we'll use that lease request, but maybe we could also take advantage of the worker reuse policies that we've talked about before. Okay, and then finally, we'll actually send out that lease request. Okay, so those were the main optimizations I wanted to talk about with Ray, and hopefully that gives you an idea of how the Ray scheduler works. But I just wanted to quickly summarize like what we've talked about today. So hopefully you've seen that like Ray can speed up your distributed applications, and it has a lot of these optimizations that in other systems you would have to really think about or even implement yourself. So we've talked about like worker reuse. We've talked about like resource-based scheduling. We've talked about data locality, and we've sort of shown how Ray's architecture can allow you to get all of these features with very, very little overhead in scheduling. It's able to schedule tasks dynamically. And we can scale out to hundreds of thousands of tasks per second, and hopefully even more in the future. Ray is built so that it can work on top of other distributed systems, or hopefully even improve the performance of some of the systems that you're already used to working with. A couple of takeaways if you've maybe got lost or stopped paying attention halfway through. Like a couple of things to probably just really remember. So like there are a lot of features we've talked about here. If you're considering whether or not you want to use Ray, like I would highly encourage you to think about these features, think about whether or not your workload can take advantage of them. And, maybe think about like how you would maybe get some of these features if you were to pick a different distributed system. Also, like we've talked a lot about details here, and if you're not a distributed systems expert, these are things that you may not really want to think about. And I think like that's one of the things that we work really hard on is to make sure you don't actually have to think about these things. So hopefully you have a bit of an appreciation for these now. But in order to take advantage of all the optimizations we've talked about today, all you have to do is use your ray.remote decorator that you're already using. And all of these things are sort of happening under the hood. And as long as you keep updating to the latest versions of Ray, these are the types of things that will just improve beneath you just because you're using Ray. And so you don't have to be a distributed systems expert to reap all the benefits. Finally, like for the experts out there, hopefully like you now have a better understanding of Ray, and you can use it to, improve the applications or libraries you're working on. All right. So that is all I have for you today. Thank you. And I think there's a little bit of remaining time, so I'm happy to take some questions now.